All right, let's get into it. So picture this. You've just installed a brand new solar panel system. It looks absolutely perfect. But then, when you run those final critical safety checks, something's off. A key test fails. Today we're basically going on an electrical detective hunt to find the single hidden fault that could mess up an entire solar array.
And that's pretty much exactly what happened in the case we're looking at today. A test installation that really should have passed with no issues didn't. Instead, it gave back results that were, as the eFix team said, inconsistent to say the least. A reading dropped below the safety limit, the test failed, and that's what kicked off this whole investigation.
So the problem is what's called an insulation fault. It's like a tiny crack in the system's armor. Now, in this small ground-level setup, finding it is, well, it's doable. But just imagine this same exact fault on a giant commercial rooftop or a massive solar farm with thousands of panels. It's literally like trying to find a needle in a haystack. A huge waste of time and money.
To solve this mystery, we first have to understand the test that failed in the first place. It all comes down to something called insulation resistance. So what is it exactly? And why is it so incredibly important for solar safety?
Insulation resistance testing, or IR testing for short, is a safety check you absolutely have to do before a solar system is ever switched on. Its job is pretty simple, but it's crucial. It makes sure that all the live electrical parts are totally sealed off, or insulated, from the ground. This is what stops electricity from leaking out, which can cause power loss, fry expensive equipment, or, create a really serious safety hazard.
And solar systems are especially sensitive to these kinds of faults, way more than your typical home wiring. I mean, think about it. As long as the sun is out, you've got high DC voltage running through the system. You have these super long cables stretching all over the place, which just increases the risk of a leak somewhere. And the whole setup is just constantly getting hammered by the weather, rain, humidity, heat. To top it all off, the brain of the system, the inverter, is literally programmed to look for these faults and will shut everything down if it even suspects one.
So just ignoring a bad insulation reading? That's not an option. It's not just about losing a little bit of power. You're looking at constant alarms from your inverter, isolation fault, earth fault, and it'll just keep tripping itself off, which means zero power generation. And most importantly, it's a huge safety risk for anyone who has to work on that system. The bottom line is, this failure has to be found and fixed, period.
Okay, so we know how serious this is. It's time for our electrical detectives to open up their toolkits. The very first step in any investigation like this is to confirm the fault is real and gather some early clues.
And this diagram shows the setup perfectly. You disconnect the solar string's positive and negative cables from the inverter, and you hook them up to the IR tester. The tester then shoots a high voltage, in this case 500 volts DC, down the lines and measures how much of that electricity leaks to the ground. In a perfect world, you'd have super high resistance, which means zero leakage.
And the results come in, and wow, they are crystal clear. The positive line passes with flying colors. It's showing over 100 megaohms of resistance. Think of that like a perfectly sealed water pipe with absolutely no drips. But the negative line, it's down around half a megaohm. Since the safety minimum is 1 megaohm, that is a hard fail. We've got our problem. Kind of.
But here's the catch. This test is fantastic for telling us that there's a leak. It even tells us it's on the negative side of the circuit. What it doesn't tell us is where that leak is. It could be anywhere along that string of 6 panels and all the cables connecting them. The mystery is still very much alive.
And this is where most standard testing just hits a dead end. But luckily for us, our detectives have a bit of a secret weapon in their toolkit. It's time to bring in the advanced tech that's going to crack this case wide open.
This really is the million-dollar question, isn't it? Is the fault in the first panel, the last one, some random piece of cable in between? Without a smarter tool, the only way forward would be to start taking the entire system apart, piece by painful piece. But yeah, there's a much better way.
And here it is, the hero of our story, the ground fault locator, or GFL function. This is where things get really, really clever. All you have to do is tell the instrument how many panels are in the string, in this case 6. It then does its thing, measuring tiny voltage variations along the string. And by analyzing those little differences, it can calculate the exact distance to the fault. It's super simple for the user, but there's some seriously complex math going on under the hood to find our needle in the haystack.
So the test runs, the machine crunches the numbers, and in just a few seconds, it is ready to spill the beans, to reveal the exact location of our single hidden fault.
And there we have it. The results are in, and they couldn't be more specific. The fault is at the negative connection coming out of module number 6.
The GFL just narrowed the search from an entire solar array down to one tiny point. Now it's time to go and see the evidence with our own eyes.
So, guided by that data, the investigator walks right over to Module 6. And what do they find? A very suspect MC4 connection. The back nut on the connector is loose, a dead giveaway that it wasn't installed properly. This is that aha moment, where the digital reading on a screen leads you directly to a physical problem you can see and touch.
So case closed. The cause wasn't some dramatic panel failure or a cable chewed by a squirrel. It was simple human error. An MC4 connector that wasn't put together right with a loose back nut. That tiny mistake created a pathway for moisture to slowly creep inside the connection, which then wrecked the insulation and created a path for electricity to leak out. And that's what caused our test to fail.
Okay, so we found one bad connector on one small system. Big deal, right? Well, why does this one little story matter to every single person who owns or installs solar panels? Let's zoom out for a second.
See, it's really important to get that while our culprit today was a bad connector, that's just one of the usual suspects. Insulation on cables can get sliced during installation, the back sheets of the modules can get nicked, and yeah, even rodents chewing on cables can cause the exact same fault. These kinds of issues are way more common than you might think.
And that's exactly why this kind of testing isn't just a one-and-done thing you do when the system is new. Insulation doesn't last forever. It slowly breaks down over the years. Running regular IR tests as part of your maintenance plan can catch that decay before it becomes a real problem. It helps you spot moisture that got in after a big storm. And ultimately, it just keeps the whole system reliable, preventing those sudden, annoying shutdowns and, most of all, keeping it safe.
So I guess the final takeaway here is this. Your solar panel system is built tough, designed to last for decades out in the elements. But its electrical health all depends on perfect insulation. That small hidden fault we found today could have turned into a huge headache down the road. It really makes you ask the question, your system might be making power, but is it truly safe? Because in the world of solar, prevention isn't just better than the cure, it's the only way to guarantee decades of safe, reliable, clean energy.